there was one time when we checkmated the geotechnical engineer, and I have to relay this one to you, see you might get quite passionate about this. We had a job where we designed a job, sort of something like that, with your car sitting there, and it was quite a steep bank. That's a car, it's not very good. You guys are students, you can relate to a car looking like that. Yeah, okay. So I can't speak to cars. The geotechnical engineer came out of his little hole, it was a he, and he said, no, you can't do that, I want a better slope that looks like that. Alright? And you're like, oh my goodness, you're just thinking dollars, dollars, dollars. First of all, you got to cut it out. Secondly, you got to get rid of it. Blah blah blah. And it was along most of the road. It was very much like that all the way. And I'm sitting there going, oh, I'm going to have to tell my boss. And I told my boss, and he stood there for a minute, and he said, what about benching? And benching is where you do this. Benching has the advantage of letting you do it steeper. Okay? So, okay, there are some additional costs in drainage at each point, but it allows you to do a lot steeper, better slopes. Some examples might be going over the Kaimais to Tauranga. You'll see benching all the way up there on the steep slope. And it does depend on what type you've got. But I remember watching the face of the geotechnical engineer drop, and he went back to his desk because our benching ended up being about the same cost as the batter slope. So you can get around it. Because of that, it's a question in interest. And we talk about benching here. Benching is often advisable in cuttings. 3 metres wide benches every 6.1 metres of vertical height is a common practice.
Which one is better?
Well, if you do this, definitely this. I've only sketched that. You might even get away with steeper. You might even get away with something like that. Which means you've got no earthworks at all to do, you know. Okay? You follow the line of the existing ground. There's some typical cut and fill batters as well. Now we're going to keep talking about my geotechnical engineer next week when it comes to volumes, because that also affected our volumes calculations. Anyone that's done any geotechnical engineering will know that every soil, has a different compaction factor, and we will talk about the compaction factors and relate that also to working out our volumes. In fact, it's probably quite a good time to refer back to a little drawing here, this one here. So next week we're going to be looking at this in more detail, and the way how we do volumes is, first of all, we work out the cross-sectional areas. By the way, that's the fifth thing that's different on your cross-sections. You can't really do an area for your cut and fill on your long section because it's got a stretched vertical, and because the vertical's been stretched, the area means nothing. But on the cross-sections, the areas are 1-to-1, so they are perfect. So we should include the areas of cut and fill on our cross-sections. Each one, surveyors take note, you've got 11 of them to do. Okay, now having said that, the engineers and surveyors for project 1 and 2, here's our platform. Let's just say that our fill is like that and our cut is like that. This is only an example. I haven't actually done the exercise yet. Let's just say it's like that. then in order to do a volume, you're going to need, well, you already will be doing this one through the middle of the platform. So you've got one done. But I would like to see you do, actually, which way will we do them? We'll do them this way. The good news is I only want to see a little drawing like that. That's all. Each time you do a section. Now, from Ingrid's class, if you draw around here, you can work out an area. You know that, don't you, with the P-line? So, as you do each one of these sections, it'll give you a different area. And you can work out a chainage along here, starting from one end. 1, that might be 2 metres, that might be 5, that might be 6, that might be 8, that might be 10.5, it might be 11 or something like that. So you've got a chainage as you work your way along. So it's a bit like those sections I showed you of the road. And the way how we work out our volumes is we have a distance between each one. We have an area of each one. And we can work out our cubic metres from that. It's not quite as easy as that. I will introduce you next week to the Prismoidal calculation sheet, my famous one. You'll get to take it home in a spreadsheet. And when we enter these values into it, it pops out an overall volume. It's the same formula on that sheet that 12D uses, Civil 3D and MX Road. But what I'm giving you a bit of pre-warning to is I'll go over this in more detail next week. In order to calculate the volumes, it's worth 2 marks. And we'll show you that as well next week. You will need to do these little sketches, about 8 of them, with the volumes under each one. And then you'll need to put it into the Prismoidal calculation sheet and put that, copy-paste that into your drawing. Therefore, I will be able to check that and check that you've done the calculate the little drawings like that correctly. Please don't get that confused with the 2 cross sections you need to do. I want 2 very detailed cross sections, trees, platform, cut, fill, all that sort of stuff on it. But these little ones, which you didn't know you had to do till this week, is what we're also going to be showing you next week. You understand that?
Excuse me.
Yep. Simon 2.
Yeah. Is there any kind of a program that using kind of integration or integral to use that volume?
To get this volume up here? Yes, it's a spreadsheet, which I'm going to give you. You put the values into the spreadsheet, and it gives you an overall volume cut or fill.
On Excel?
Yeah. Don't worry, it's not as easy as you think. But the good thing is I make you remember the formula for the test. Okay, so some of the things I talked about here, I've also put in an explanation format, and I've also put it in a, I'm sorry, I'll go on to the actual, where it is. I've got a whole list of terminology, which is very good questions for the test. And some of the things I've talked about, for example, there goes the benching. And another one which is very important as far as I'm concerned with roads is the berm, or the side of the road, and even more important is the shoulder. So there's some little sketches here that go with each one, and there's some explanations of the different things. Some of these I've questioned in the test, some of them I haven't. Now I want to talk briefly about the shoulder of a road. The shoulder of the road is probably the most important structural part of the road. A lot of people think it's just there in case you have a flat tyre or in case you have to pull over and there's an accident and an ambulance can drive along it or a tow truck. It's actually there for the strength and the integrity of the whole road. Without the shoulder, the road will start to disappear down the bank or into the side drain. Sometimes you'll see a truck lying on its side and you go, how the hell did that happen? What sort of guy would drive a truck on a straight road and then just woof, flick it onto its side? It's not the truck driver's fault, it's the fault of the road design because the shoulder has given way. And see, cars don't make a lot of difference to our roads, it's the heavier vehicles that do. And he's parked or he's pulled over to the side and bang, the whole lot's gone down the side of the road and flipped him. So next time you're trying to pass a truck and you're getting really frustrated with him because he's not going as far to the edge as he could, there's a very good reason for that. So the shoulder of a road, and this is one of my multi-choice questions, is all to do with strength. So I'll throw answers in there like a good place to park if you have a breakdown. Yes, it is, but it's not the main reason for it. And also for emergency vehicles, etc. So you kind of, when you're designing a road, you work backwards from the shoulder because you need the same strength all the way to the edge of the shoulder, which basically is the edge of the cutting for a platform or for a road. So therefore the geotechnical engineer's got all the rights to go right to the edge with his design before he comes up with a better slope design. Crossfall's an interesting one. I'll go back to this sketch here. One or two of you might have an interest in cars. Obviously I don't. So I would have drawn you a good one. But I do occasionally watch shows at Dixon, going round around the track, making you giddy. Those tracks, just like the bike tracks in the Olympics, they always have a very good circular curve on them and a very good camber on the road. And you'll notice that the camber starts at about 3 degrees both ways. Then it works its way to a situation where it's got a full camber from here to here, and then it'll go back to its -3 degrees on both sides. And that is basically goes from the start of a circular curve to the end of a circular curve. On more complex roads like motorways, we have a spiral curve leading into the circular curve. Engineers will go on to do that in highway design, motorway design as well. But that's just a basic drawing introducing you to super elevation and camber. Okay, there's various little sketches there, pretty much repeating and covering things. One thing that I'd like to point out here with this sketch is we normally have a subsoil drain under roads. So if you're ever in an office drawing up these typical sections, you need to include a subsoil drain. Now, I haven't decided yet, but I may get the surveyors to do something like this, which would be classed as a typical cross-section, because when you do road design, normally they do a typical cross-section in detail to show what's actually there, and that would be a very good example of a typical road cross-section. Lastly, I've included this little sketch here. If you see a carved out piece of ground ready for a road, on the right hand side you'll normally see, or left hand side of the road to where you're driving, you'll normally see 1, 2, 3, 4 pegs. And they're the pegs the surveyors have to put in. They peg the bottom of the batter, they peg the point at which the cut and fill equal each other, and they peg the piece at the top of the batter. Bottom of the batter we know is called the toe of the fill, and the top is called the top of the cup. And there's also one last peg here, this excavation peg, which often they have a board with the angle of the cut on it as well. So I just wanted to include that, because when an engineer sends a surveyor out to do a job, that's the sort of thing that they need to see in the ground before the digger starts doing the donkey work. There's a question on that as well. Now, lastly, we'll go on to look at some examples of cross sections. I've got these in a better format to look at, so we'll open them up. Now, just remember, like all my examples, it's not perfect. You copy it, you're more likely to get about 50%. Is there anything there that stands out as being wrong right from the start? What did I tell you about the hatching? Rock conglomerate. It is not a hatch for fill. Secondly, those arrows are not the right size. So what that student did is they forgot to change the arrow size for their cross sections. Minus 0.5 would have kept. They haven't labelled their batter slopes properly. The two should have been on the top and the one below. And the fill should be pointing at the batter slope. At the fill. That's fine what they've done there with the fill volume and the cut volume. And they haven't got their ground line right. They didn't look back on their TechLit notes. It's on a 45-degree angle. Trees are okay because their other trees were stretched on their long section. Now, with the cross sections, a common question I get from students, won't be getting it this year because they'll say, refer to your movie from my lecture. Common question is, how far do we take the cross sections? And my answer is, as far as you like, because you're only going to get so much of it fitting onto the sheet. Now, in this case, we had an outlet, lovely outlet structure there, by the way, completely wrong. And we had a manhole, just like you guys have got, over here somewhere. Now, I said to all the students, just like I'm going to say to you, the platform and the outlet, if you can get both of those in there, then you've done your job with your cross section. Okay? Platform and. So, the way how we cover the manhole is we do that symbol, that the students got the symbol right. So they were listening to me a little bit. That means it carries on. What the student didn't do is say to manhole 1, or A, invert level equals, lid level equals, bottom, what else we got? Bottom of manhole. Equals. So that can also be covered. You could also say C note 3 or something, and in your notes you could say manhole blah 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 blah. So you don't have to write all that on there, but you do need two manhole A or B or C on there as well. So that's what the students left off there. This height of the text is wrong, along with those arrows at each side. And look where they started their distance. Obviously not listening in class. I don't think that will get half marks. Looks pretty good when you opened it up. Lovely downloaded internet trees. My daughter trying to do a big picture on the front page of her English assignment in the last year at school. Wondered why she got very low marks. Lovely sketch though. Okay. pool too. This time the student listened to me and they did a centre line. That's cool. But they didn't do a distance down the bottom. Instead they thought they could just do dimensions. No, that's wrong. So, no dimensions. All of these are sideways and they've got M after them. I didn't ask for that. Should be the other way around, not that way around. Wow, they really did like their basket weaving, didn't they? Absolutely overboard. You only need to show a little bit of it so we know where it is. So for example, here is important, plus on the other side, maybe a little bit under the pipe here and here and here. When I say a little bit, about that much. They've used the batter slope symbol there, completely wrong. It's used on the existing site plan, as per my sketch a couple of weeks ago or a week ago. The tree was wrong. They copied the tree from their long section and didn't stretch it down to the right size. And for some reason, they thought because this little triangle was very small, they were allowed to get away with very tiny text. And they did that at 1:1 as well, not 2:1. So a lot of things there that meant that even although they went all the trouble with the notes and everything else, there was a lot of imperfections with that one. Now that was the section in one direction, and by the way, there's no outlet as well. And I could keep going. On a cross section, we don't show a centre line. Not 100% true. It depends how the pipe crosses the cross section. In this case, the student just drew the line all the way, but the pipe actually crossed over the cross section like that. So the only piece that was solid was the bit where it crossed over, where you cut through the pipe. The bit behind, we're not interested in, so they shouldn't have even shown that. Where it crossed over, there should have been a centre line in both directions, like in your sketch for Ingrid in week 2. And then when it was in the distance, it was dashed with no centre line. Got that? So you have behind, don't show, cross through, solid, a centre line in both directions, and in the ground, dashed each side, but no centre line.